as well. Okay, so I've started the recording, so it's the review session for the final where I can see what types of questions you guys might have. Okay, so what can I help you with?
No. See, the way you think about it is you always line up.
Are you sure? Because
with your axes.
MG has to, or net has to be less.
Okay, so I'm hearing somebody on Aaliyah's.
Yeah,
The
only the vertical
angle.
component.
The vertical component of the N is going to be MG, but there's also a horizontal
Hello.
Yeah, hey Aaliyah, how are you?
Hey, fine you.
Yeah.
Good. Are there people talking in the background where you are?
Yeah, sorry about that.
That's all right. What we may have to do though is have you type in your questions because I think it's going to be hard for us to hear what you say.
Okay. How do I turn it on? Oh, okay. I just mute it, right?
Yeah, correct.
All right.
Cool. All right, so you guys can type in some questions, or if you want to try to work through one of the review problems, whatever you want, we can do. Was everybody just joining in to see what other people had to ask? Okay. Because I was told people who do that are called lurkers. Sure, let me try to take a look at what 16162 is. Okay, so for problem 16162, so hopefully you guys can kind of get to your books, but essentially what it is, it's got a square plate. So it's got something basically like this, and it's in a couple of slots. Okay, so there's point B is right here, and it's in a kind of like in a vertical slot. And then point A is right here, and it's going to be in a horizontal slot, and you're given that this angle right here is 30 degrees. Okay, so hopefully you guys can get to your book, but essentially that's a poor drawing of what it's saying. And so it's got sides that are 150 millimeters, so 1.5 meters, and it's a square. So all of those are there, and you're given that the mass is equal to 2.5 kilograms as well. Okay, so it's released from rest in the position shown, and we're asked to determine the angular acceleration of the plate and the reaction at corner A. Okay, so everybody think for a second, what type of problem would this be? Okay, so what we'll do is I'll just kind of wait, and then like the count of 3, you can type in. Okay, so think on your own. This is problem 2 on the final exam. What is your type of approach? What's the principle that you're going to apply? Okay, so count of 3, you guys type it in. Have you had enough time? Okay, 1, 2, 3. Type it in and hit enter. And Delaney left, or somebody left maybe. Yeah, so it's going to be rigid body. So Aaliyah's the only one who's typed anything in. So what do you mean by constrained motion exactly? Does that mean just like kinematics, right? So the question is it just kinematics, or do we think we're going to have to figure out some force type of stuff? Yeah, and Ali is correct. We're going to have to worry about the forces here, right? Because we haven't been, usually for these types of things, if we were doing a kinematics, we'd have to be told something like, A is moving to a left with a constant velocity of 6 meters per second, and then figure out the velocity of B. So you have to be given a lot more, right? We don't know what the velocity or acceleration of point A or B or really anything is going to be. It's all going to be driven by really the weight and the constrained motion like what Aaliyah's talking about there. So this is going to be kinetics type of problem. So then you have to figure out, right, am I asking, is it work energy or not? So what do you guys think? Yes to work energy or no to work energy? Okay, good. So yeah, because it's not asking for two different locations, right? So it's saying it starts from rest and what's that immediate acceleration right after, right? So if it was a work energy, it'd be something like, what is its velocity or angular velocity when the block is horizontal? You know what I mean? Like when AB is down at the bottom. Okay, so great. So it's an F equals ma type of problem. So we all know our first step there is to draw out our FBD and our KD. So I'm going to give you just a second to do that on your own. So you guys should all kind of take a piece of paper, draw out your FBD and your KD, and hopefully you can draw them a little bit neater than what I've done here. Okay. So if I'm looking there, when we have kind of this plate, and these are, like rollers there essentially. So that means at A, I'm just going to have some sort of upward force, and I'm just going to call it A. You can call it F of A or whatever, right? And then right here, I'm going to have a force B. Okay? Are there any other forces going on there? I should tell you though, so a couple of things you should look at. One of them is it says it's in a vertical wall, right? So and that's something you could ask on the thing. You can ask, is this in a horizontal plane or vertical plane, right? So then we're also going to have an MG here. So there's my FBD. And then if I come to my KD, right, I'm going to just go ahead and do the same old thing that we've done a bunch of times before, where we have MAGX, MAGY, and I've got some sort of IG alpha. Okay, so what is that it? Do I need anything else? Yeah, I need my coordinate system, right? So I need to make sure I label the X and the Y. I don't just kind of draw arrows. I want to label my X and Y. Okay, so the question that we had there, are there X component reaction forces at A? And no, that's just a roller, Chris. So does that make sense to you? Remember you did that some in statics too? So if you have a roller, then that means at point A here, sorry, I should have drawn like a little roller thing. So if the picture is probably a little better in the book. So basically it reads that the motion of a square plate of side 150 millimeters and mass 2.5 kilograms is guided by pins at corners A and B that slide in slots cut in a vertical wall. Immediately after the plate is released from rest in the position shown, determine the angular acceleration of the plate and the reaction at corner A. So basically, at point A, that thing can move this way and that way, so there's no force resisting motion in that direction, right? You could end up saying, is there friction, in which case there would be. But in this case, we would assume that it's smooth, okay, because there's a roller. So B can only move up and down in that direction, so there's no resisting force in the other. Okay, so now, is everybody all right with that? Any questions there? And Matt, can you hear me as well? You can type in the chat box is what we're doing right now. Cool. All right. So, and Matt, we're working on problem 16-162. We've already decided that it was a rigid body kinetics Newton-Euler type of problem. Okay, so I did my FBD, KD. What's my next step? Yep, so I'm going to do equations of motion, some of my forces, some of my moments. Okay, so if we do like a sum of forces in the X equals M, and is this big enough? Can you guys see my writing all right? Okay, good. So we do sum of forces in X, and so these aren't too bad here, right? You got a minus B equals MAGX, and then if we do sum of forces in Y, that's going to equal MAGY. So if I look there, it's just going to be an A minus MG equals MAGY. Okay, so right there, that's one equation. All right, I'm going to put that as 2 because I got one equation up here. Okay, so now I can do sum of moments about A equals IA alpha. And then how do I sum moments at A? Is anybody going to stop me there? Yeah, why not use G? So I can always use G. Can I use A here? Anyone else? So Matt's got a yes, and then I paused. So then he decided no. What do you think, Matt? Okay, so I'm gonna go 2 things. So first of all, A is not a fixed axis of rotation. So Matt's second indication is correct. I cannot use that, okay, because it's not a fixed axis of rotation. So remember again how we talked before is I'm always okay to do sum of moments about G equals IG alpha. Okay. And then, Eileen, if you remember, I mean, it's kind of okay, but if you do that and you draw it, then here, right in my equation 1 and my equation 2 down here, I'm going to have to put a minus sign. Okay, so if you remember kind of how I've always tried to do it is to assume it's going in the positive, and then I look and see, okay, because I think your intuition's great here, right? Yeah, it's kind of makes sense. It's going to accelerate downwards, probably going to accelerate to the left, okay? But it's a little bit easier if you just stick with the sign convention and then check it after you get your algebraic answer, because sometimes it just gets too hard. Like if you draw it to the left and then you get a negative answer, once you solve out the algebra, then that means it's to the right, which is in the positive X, and I just get confused, right? So I never like to say it's not okay. I just try to tell you what I think is usually the easiest to keep track of. So you can do it correctly by doing what you're saying. I think it just ends up being a little bit harder to keep track of. Do you understand what I'm saying there, Leah? Okay. All right, so like we just said, you can do sum of moments about G equals IG alpha, or I'm going to write above there. I could also have done sum of moments about A is going to equal IG alpha plus R, and that's going to be to G from point A crossed into MAG. Okay, so you can use either one of those equations. You just can't use both of them. Okay, so this one's going to give me my third equation. Okay, are there any questions there so far? Okay. And so Matt said, can we sum moments about a point with a constant velocity? And you actually can do that, but I'd say you really have to be super careful there, Matt. That's a little bit more advanced, so I would caution you against doing that. If you decide you're really sure about it and you can go with it, then make sure you write that on your paper. No, it's not the same, Matt, because the one I wrote was sum of moments about A equals IA alpha, right? So this equation is not the same as this equation. So this one up here is okay, right? That's got totally different terms in it than the one below. Okay. Do you see the difference there, Matt? So the IA is what we would do. We would find the using the parallel axis theorem. So you can only use that one when you have a fixed axis of rotation. Okay, so right now we've got 3 equations, right? And so if I sum moments about G, then I'm just going to have to figure out that trig, right? And that trig's a little bit of a pain, but it shouldn't be too bad, right? So if this distance is 150, right up at the top, then I've got a force B going right there, right? So now I just have to figure out what the distance is, right? If I'm going to G, I have to figure out what that distance is right there, okay? Okay, so basically, let's see here. What is that going to be? I'll probably have to do a bunch. Let me see if I can go down or not with this thing. Thought I could go down farther. Yeah, maybe not. I'm going to get rid of, sorry guys, I don't use this one as much. See if I do a view here. Yeah, that's not doing it, is it? Shoot. That's just making it worse, isn't it? Let's see here. I thought I used to be able to go down a little bit more. Sorry there, guys. What is R cross MA? That's just like MAD. So if you don't, like at this stage, if you don't know that one, just do it about MG. Okay, that's something we had talked about a while ago, a couple different times for one. So don't worry about doing that. Just always, you should probably always some moments about G. But it's really no different than what we did for angular momentum when we did R cross MV. Okay, so basically then you're going to have to figure out you know, what this distance is, like I was saying there, for B, and then you're going to have to figure out what that distance there is for A. So that's going to give you some moments about G. So now if I look, I've got, you know, for this one, that's my third equation. So I don't know if I go over here and say, well, what are my unknowns? Well, my unknowns are going to be A, I don't know B, I don't know AGX, I don't know AGY, and I don't know alpha. Okay, so I've got 5 unknowns and I've got 3 equations. Okay, is that makes, so I'm going to call that dy, I'm going to call that dx. Okay, is everybody with me so far? Aaliyah, this was your question, right? Are you guys feeling all right in the room you're at? Yeah, I mean, so I think it would take me a minute to try to go through the like the dy thing, but essentially that one's, let me see where I'm going to write that up top here. Okay, so this is going to be your sum of moments about G there. So it's going to be it's going to essentially be a minus AY times that dx, and it's also going to be a minus BY times a dy distance. I'm sorry, that BY, I don't need a Y there, right? Okay, and then, so this dy is a little bit easier probably to figure out, right? Because if that whole thing's 150, then we can figure out there's that theta. Do we say, yeah, 150, so it's going to be 75 times like a cosine 30 there. Right, so I just have to figure out what that distance is right there, right? So that's going to be 0.075 times cosine of 30 degrees. Does that make sense? I do that all right? Yeah, so it's going to be a bit of trig is a little bit of a pain, right? But you know, so that's what's going to be the pain for this one, as I was saying. Okay. So can I keep going, or do we need more? Do we want to try to work out the full trig thing? Okay. All right, so now I've got 3 equations, I got 5 unknowns. So what am I going to have to do next? Any ideas?
Holy shit.
So Bryson, you guys might want to mute yours because I can hear all the background noise there. I think that's yours. Yeah. Cool. Thanks. All right. So yeah, we got to do kinematics, right? So don't forget, most of these kind of things really follow that same deal where we got to do, you know, whatever our kind of our diagrams are, right? So we do the diagram, then we end up doing our equations of motion, and then we go through and we've got to do our kinematics. Okay. So I'm going to have to add a new page here. So let me go to this, and hopefully you guys have that same kind of problem up, but essentially we've got this was our point B, and then this is our point A, right? And we had our center mass up here in the middle. This was 0.15, right, as we went through there, and it was a square. And then this was 30 degrees. Okay, so like we said, we need to do kinematics. Okay. Get a little bit of feedback, so I think somebody else might need to mute their microphone as well. So then we're going to have, right, so this is G here. So what points might I end up doing here? What points could I end up trying to relate with kinematics? Okay, so I can do A and G. So let's do like acceleration of G equals acceleration of A plus omega cross R G with respect to A, right? Plus I've got alpha cross R of G with respect to A. Okay, and what do I know about omega? So omega 0 because it starts from rest. And then do I know anything about acceleration of point A? It's only in the x. So I'm going to write it out like this. AGX in the I plus AGY in the J. So Leah, I'm going to go back to what you had talked about. If you drew in your kinematic diagram, your kinetic diagram, with those things going the other way, then you'd put negative signs here. So to me, it just ends up getting a little bit confusing. So I'm not saying you can't do it. I'm just saying that maybe you should. Okay, and then I'm going to say, okay, then A of A is only in the x direction, right? So I can do an A sub A in the I hat only, and then I have plus, and I know that alpha is in what direction? So I got to go back to my kinetic diagram, remember? So I'm going to skip back. Oops, attention, my kinetic diagram. Where did that end up? Okay, so if I look at my kinetic diagram, I drew alpha, and what direction's that in? Yeah, the positive k. So I'm going to do a k there, right? And now I need to just figure out, okay, what is this, what's the x and what's the y direction here? Okay, so I'm just going to write it out that way because if we spend too much time on the trig, we won't get to any other problems. Okay. Yep, and omega is 0 because it starts from rest. Thanks, Matt. Yeah, that we're actually working 16.162 if you came in a little bit late. Sorry. So those are just some of those keywords, right, that we always look for, and a lot of these problems tend to be that way. So they'll give you the omega. Otherwise, we have to say it starts from rest, which means omega is 0, or it'd have to give you some sort of omega, or you might have to find omega by doing like a work energy, right? Some of those multiple step types of problems. Okay, is everybody all right with me so far? All right, the problem now is, right, so I've got kind of two more equations. So if you remember from the previous page, we had 5 unknowns, and we had 3 equations, right? Sum of force in x, sum of force in y, and sum of moments. And our 5 unknowns were a, b. We didn't know what agx was, we didn't know what agy was, and we didn't know what alpha is. Okay, so luckily this gave us 2 more equations, right? So plus 2 equations, which we have here, right? So this would be like equation 4 and equation 5, because I have an x and y component. The problem is I introduced another unknown. I don't know AX, right? So that's a big hassle. So now I have 6 unknowns. Okay, so now I have 6 unknowns and I have 5 equations. So I better come up with some sort of other equation. Okay, are there any ideas there? I need some more equations. What am I going to do? So we have one relative motion equation. And that's our related A to G. So I'm getting a little bit of feedback, Bryce. Or no, it might be Edwin. You might need to mute your microphone, please. Yeah, so now I've got to, with relative motion, so I can either do like, so you were saying B and G, right? So I could do either like A of G equals A of B plus omega cross R, right? Plus alpha cross R from G to B. And remember, it doesn't matter. I could do either. I could do G first or I could do B first, right? It's totally up to you. So now, but what do I know about AB? Thanks, Edwin. Yeah, so it's only in the y direction. So now I can do AB in the j hat direction plus, right? And now this guy's also equal to 0. It's the same omega as it was before. It's also the same alpha. So if I want, I could write AB, you know, alpha AB or something like that, but I don't really need to do that. So this is, I'm going to put like an x2I because now it's a different, position coordinate, right? But I still have my same AGX I hat and I have my same AGY J hat, right? I now have one, I now have one new equation, new unknown, right? So I can put down here, which is AB that I can also put in the Y if you want. You don't have to, right? Because you know it's in the Y. But I have now 6 and 7, right? So now I have 3 equations plus 2 equations plus 2 more equations, right? And now I have 7 unknowns. Okay, so I think Chris was asking, will we be asked to solve it through or just write it out? I don't know. Usually we won't have quite this many, but you could. And if you did, I would probably just say, you know, to write your 7 equations, your 7 unknowns, and take the 3-point hit. Don't take, you know, don't work through the whole thing for the algebra. Is I think the strategy I would do, unless I get everything done. So, okay. So does everybody understand? Yeah, you totally should do that, Bryson. You should totally write out your, you know, number of equations, kind of like what I've done here. In fact, you should go through the, you know, don't just do it quite like I did unless you're really rushed for time. What you should really do is write out every single algebraic equation. So do out your I's, do out your J's, and then get, you know, like equation in the X. So get one equation there, then do your equation in the Y, get one equation there. You follow what I'm saying? So do out your cross products and then split out your X and your Y's. Yeah, but what I want you to do there is write, you know, like kind of how you see how I've written 6 and 7 here. So you should write like this is number 4, this is number 5, and then break it out as much as you can. This is number 6, this is number 7, right? And then write, you know, here are my unknowns, and then I would just write a little note: seven equations, 7 unknowns. You solve it, professor. Okay, and so if it's me grading, you're getting like, you know, 27 out of 30. Okay, maybe even more if they're all, you know, as long as those equations are set up correctly and you've done your full FBD and everything. Okay, so Leah, you had asked that question. Is this one all right then? You kind of get that general approach? Great. So Bryson's asking, if you don't write the correct amount of unknowns and equations, will you get docked? Yeah, if you don't have enough equations for those number of unknowns. So these are pretty typical. I mean, if you go back and look at these ones we did, then for ones where you had like a fixed axis of rotation, a lot of times we ended up with 5 equations and 5 unknowns because we had sum of force in X, sum of force in Y, sum of moments. And then it was easy to solve for the acceleration of G because we had a fixed axis, right? But we had a couple different problems like this where we had to solve 3 different things because we had one constraint like here going right and the B right going up and down, and we had another one going this way. So if we don't have that big constraint, then we end up having even more unknowns. Okay, more questions. Sure. Did you have one in mind, Bryson? Okay. So you want me to just make one up? Okay, so let's do let's do something like this. We've got a bar, and let's say it's L, and I'm going to have it be a mass M. And let's really mix it up a little bit. Let's have it coming down like this. So it's a sphere coming down. It's going to hit at the very end, right? Because you're kind of asking like this. It's going to have its own omega naught, okay? And it's going to come down at a 30-degree angle, okay? And that's going to have a mass of capital M, and it's going to have a radius of R. So I think that's about, oh, and let's even have, this is going to be swinging down to hit it like a baseball bat, but it's going to stick. So that's going to be omega bar. I don't think we can have anything more. So does everybody see what's happening? So it's going to hit it smack on when it's first. So it starts, you know, back up over in here somewhere originally, and it's going to swing down through. And then right at this point when it's vertical, it's going to hit this big sphere, and this sphere is rotating, and it hits right here at this point, and it sticks to the bar. Okay. All right, so now what we can do is if we set our same old coordinate system that we normally do, it's actually going to end up being a little bit of a pain because everything's going the opposite way, but we'll deal with it. So we have an impact, so we should think, okay, this is going to be impulse and momentum, right? So what's my first step in a rigid body kinetics type of thing? Yep, so we're going to do our diagrams, right? So for this guy, and we still do, even if we're going to end up doing, let's call this point A up here, and let's call this point B down there. So even if we're going to end up doing stuff with like about a point, a fixed axis of rotation, we still do everything to start out with around the CG. So for this one, we know, right, so this is a little bit different, Aaliyah, since we know which direction it's going in, right? So we know that it's got some sort of a mass times velocity 1, so VG1 here, so I'm going to call that point G. So that's our center mass G. Okay, and then I also know the way it's going is like this, so that's going to be like an I bar G times omega, and we call that B. Okay, is that all right for what the bar is doing? Okay. And then just as the ball hits, right, so I'm going to draw this just a little bit to the side there, but the sphere is going to have some sort of an I sphere omega, and that's also going to be about its own center mass. And I'm going to have a capital M times and I call that omega naught, and let's call that V naught. Okay, is that all right with everybody? Questions there? Okay, so then I got to figure out, all right, what types of impulses are going on with this thing, right? So I've got up at the top, I've got some sort of an AX delta T. I've got an AY delta T. And then down here, I'm not quite sure the exact direction, right? Because we haven't said if it's oblique or anything. So I'm just going to kind of draw like we've done before, where, hey, here's our little ball, and we've got some sort of an R delta T for our impulsive forces. So the sphere on the rod is equal and opposite to the impulse of the rod on the sphere. Okay? And then in the end, right, then we're going to have, and we now just need to kind of decide which way we think it's going to go in the end, and then it just depends on which one's got more angular momentum in the very beginning, right? So which way do you want to assume that the angular momentum is going to go afterwards? So is a bar going to swing to the left, or is a bar going to swing back to the right? Oh man, so we got one for each. Somebody vote again so we can break the tie. To the right. All right, sorry, we're going to the right. All right, go ahead with your question too. So if it's going to the right, then I'm going to say that this is going to be an MV VG prime. Okay, and then I'm going to have some sort of an IBG omega prime. I should call it omega B prime. And then down here for the ball, right, what's the direction of the ball going to be? It's going to be to the right. Okay, so for the ball, it's going to be a big M times a V of the ball prime, and it's also now going to be going like this. So that's going to be an IS. Whoops, what did I just hit? IS omega prime. Okay, and then we had a question in the x direction or diagonal. Well, this one's a little tougher because you're not quite sure what it's going to be, right? Oh, that's nice. Okay, so so the question that Matt had, right, you guys, is what is he's saying for this guy up here, right? If I want to look up here, he's asking what is the one there, the force between the ball and bar in the x direction or diagonal. We don't really know, so we could end up sort of trying to figure that out. Since it's hitting at an angle there, it's probably going to have some sort of vertical component. We could solve for that a little bit later on. Okay, and then the thing, doesn't the ball's radius affect its MV? Well, sort of, but if we decide, right, if we say they're going to stick, right, then we want to make stuff that's consistent, right? So if the ball or the sphere is oh, I see what you're saying. Like for the other one, it depends on how big it is. I understand that question. Yeah, so because what you're trying to say is, hey, it's going to be like the radius here. Yeah, so if we do have the radius one, then yep, I agree with that. Let's do that one instead. Let's say it's going that way. I don't know if I can erase this thing or not. This one here. Now let's see. Yeah, so I'm going to get rid of that guy right there. Okay, then why did the ball rotate the other way, is what Bryson said. It's because we decided that the whole thing, after it sticks together, we're just going to assume that the ball's big and heavy, and it's going to make the bar rotate back around, right? We had a little vote there. So then we just figure out in the end, we say what we assume. So like, if you want, we can write here, like, assume after impact that that's the whole thing together rotates counterclockwise. We just had to assume one way or the other, Bryson. So if the bar's rotating around that way, then so is the sphere. Okay, so other stuff now. Everybody good so far? So that's basically got everything we could possibly want in one of these problems, right? If we draw out this diagram nicely, right, now we have to do out our equations of motion, right? We talked about angular impulse momentum, right? Because it's rigid body, so we're going to have to at least use that. So if I had asked you originally for what's the angular velocity of the whole thing afterwards. All right, so if I'm doing that, then what's my next step? What do I do next? Yep, so I need some equations. So we talked angular impulse momentum, so I have to decide what point is the best one to some moments about. Yeah, so why did you say A, Aaliyah? Yeah, because then those pin forces cancel right out. Perfect. Okay, so now if we're going to do, and it's not bad for you to just do like some moments about A, right? So if you sum moments about A, I mean, hopefully you should have time on this final exam tomorrow night. So if you do stuff like that, the grader's going to be impressed. So if you write things like that, I think it's going to help. What's one other thing that I should do to make sure the grader's impressed? Boxy answers, yeah. What else? Slip a $20 in the test. I don't know if a 20 is going to impress me that much, but you're thinking, what else? Oh, I did draw one. I'm sorry. I forgot. I thought I had drawn a coordinate system. Cool. Never mind. All right. So we're good. So we're good. All right. So some moments about A. So now we just have to look at our system, right? And so does our sphere have any moments about A? Yeah, you should just have to draw one, just draw one coordinate system, Bryson. You want to do it reasonably close to your diagram, because remember, again, I don't want to make excuses, but we're grading, 200 something of these. So if it's not immediately apparent, we might miss things. So you want to make sure we don't miss that type of deal. Okay, so I'm on sum and moments about A, right? Then does the sphere have any angular momentum about A? Yeah, and in this case, it's going to be like a capital M, right, times V naught times cosine 30 degrees times L. Okay, so what that means is, remember, it's a perpendicular distance, so it's hitting it right there, but not the whole thing is going perpendicular, right? Only a component, really only the X component of it's going. Right, so first is, are there questions about that? I thought we might have done like a bullet hitting a square plate or something. M is the mass of the, right, M is the mass up here of the sphere. Okay, the capital M is what I said for it. Okay, and is that plus or minus? Yeah, well, so you could look at it either way, Leah. You could either say that's a perpendicular distance, or you could say it's the x component of this thing, because, you know, the x component would be like right here, and that's going to be a cosine 30, right? And it's L away from point A, right? And then the sine 30 is going to be right here, right? That would be the sine component, but it goes directly through point A, so it doesn't contribute a moment. So you can kind of look at it either way. You know, that this would be, you know, that would end up being the perpendicular distance right there, which would be L cosine 30, or you could do what I just did with the velocity there. Which equation do you mean, Aaliyah? That's also like R cross MV. You could do it that way as well. Do you guys want me to show you the R cross MV? Well, yeah, so I'm not quite saying conservation yet, so because I want to work it through to make sure that it is conserved. So if I draw a good impulse momentum equation, then it'll tell me if it was or not. Yeah, there could be a Y component, yeah, depending on wherever it was hit, Luke, yeah. So I could have to do an X and a Y component, right? Because if I did, let me just do this one really quickly. If I did the R cross MV type of thing, then my R would just be L times J in the minus direction, right? And then that would be crossed capital M times V naught cosine theta in the I hat, and that would be minus MV naught sine theta in the j hat direction, right? That would, does everybody see what I'm doing here? So that's just the R is going from here down to there, and then my velocity expression would be this. Oops, yeah, that's right. So there's my velocity. Well, J cross J is just 0. And then if I do L, right, if I do J cross I, that gives me a minus K, but then I've got a minus out here. So basically now I get what we talked about before, where it's capital M times L times V naught times cosine theta, which is what I have right here. Okay, so does the sphere have any other angular momentum? Yeah, because Bryson wanted everything, right? And this is going to be now minus because of how I said it was rotating here with this omega where it's going clockwise. So that's going to be now like an I of the sphere, right, times omega naught. So that's this term up here. Does the bar have any angular momentum? About A. Yep. So now I've got to see where that MVG is, right? So I've got an MVG1, which is perpendicular distance to point A. L over 2, and is that in the plus or minus K hat direction? Yep, so that's going to be a minus, right, because it's going to be like that way around. Yep. And then I have a minus IBG omega B. So this whole thing is for the bar. Now, I could also have done the bar as just being the parallel axis theorem like Matt's suggesting, right? So remember we showed that before a couple different times now where it's the same thing. You just have to be really careful that you don't get confused. So like I said, I think on a bunch of these different problems, I've tried to work it multiple ways, and I know that gets confusing. But you should be able to kind of break that down for yourself now and say, okay, I can either do it this way or I can do the parallel axis theorem. Just be really careful that you don't do both. Okay, and then I look and I say, okay, well, what are my sum of moments here, right? If I do my sum of external moments about point A, then does the AX delta T cause a moment about point A? No, because it's just like Aaliyah said, right? She said, hey, it's not that, it doesn't cause any moment, right? That's why we chose point A. And then what happens to the R delta T terms? They cancel out, right? So essentially what you see kind of all this huge thing there, right? That whole thing there is my angular momentum about point A immediately before the impact, like 1 millisecond or 1 microsecond before. So Matt's asking point-wise. I mean, so it's always good to communicate things. I don't think I would take off, so it's a little bit on how rushed you are. So, I mean, you could certainly say plus, it wouldn't be a bad idea to put +0 just to see that you know the whole type of thing there, right? It's always not a bad idea to put, an mg delta t basically equal to 0, but I know you're going to be a little bit rushed there, right? Okay, so that's all the stuff before it, right? So this thing here was just R cross MV. So let me see if I can get some colors here now. Okay, so that was all before. So now we're going to say all of that stuff is equal to, and now this is going to be after. Right, so we could potentially do one big old parallel axis theorem, like a little bit like what Matt was talking about before. But if I look up at this whole guy here, right, then you guys should take a quick second and just write out what you think all that stuff would be. What would go in the second part, right? So now I'm going to have one big old expression down here. And so work out for yourself for a second. All right, so I'm going to call this is going to be like equal to D2, and it's kind of like what we worked at before, where D2 is equal to the square root of L squared plus whatever the radius squared of that thing's going to be. Okay, so that means we would have here, where this is going to be, for the first part, I would have like an M, capital M times V prime times square root of L squared plus R squared, where R is at the radius of that ball. Okay, and then that's going to be in the plus direction, right? Because it's going to go around this way. Then I have plus an IG omega prime, and so that's it for the. Actually, I should make that let's call that an S instead. Sorry, because we had the other thing we called this the G. Then I do plus. We'd have an MVG times L over 2, and we'll call that prime, right? Plus, we'd have our IBG times omega bar prime. Okay, so basically for this thing, right, let me see, I'm not sure why that got bigger. Let me, me zoom out again. Okay. So, so y negative, okay, LE is okay. So Chris is asking, why is there still an IS term? Because it's kind of like, so take your arm and swing it like below you, and so make your hand big out and wide, right? So pretend like your hand has got a frisbee on it or something. So if you move your hand back and forth, like if you move it from being vertical, then swing it up to being horizontal, right? Your hand has changed its orientation. Does that make sense? So if that thing is swinging, like when it's down at the very vertical part, it's going to have, like a line there. And then once it swings around to the horizontal part, that line's going to be here, right? So it's got some sort of resistance because it's got shape. So that's why we still have an IS, because it's actually rotating. Does that make all right sense, Chris? It's just like, because this line here, right? The bar is like this when it's vertical, and then the bar is this when it's horizontal. So everywhere between it also has some sort of a resistance to angular acceleration. So it has an I that you have to account for. If it's just a particle, like we've done for the majority of the problems, then the IS goes to 0, right? It doesn't have any inherent resistance to angular acceleration about its own CG. Okay, so this has got, just about everything, right? It's kind of like that catcher problem that we did when we did the catapult stuff. Yep, so only if it's got a significant radius. If it doesn't have a significant radius, if I don't give you like any type of R, in which case you could come ask me, right? If you don't have any significant R, you can come ask about it, or if it's like the bullet type of problem. Yep, that's correct, Matt. And of course, it's never a bad idea to write treating as a particle, model as a particle. That's correct, Bryson. Yeah, so now the question is, what would happen if I wanted to combine everything? So I'm going to do it in the blue. So if this confuses you, just go to what I have up there, right? Because what you're going to end up doing for this case, right, is you're going to have to then say, well, V prime is equal to something, something, something times omega prime, right? But that something, something, something is going to really be times this D2. Okay, so, and that's for the sphere, of course. Okay, so now if I was going to do the parallel axis theorem for the whole thing, then the sphere, it would still have just its regular old I sphere about its own G, right? Then plus, it would have its capital M. Well, what's the distance? Well, the distance is just the square root of L squared plus R squared, right? And that's going to be squared, right? So that's this would be like the part for the sphere. Okay. Then I would have the IBG, and then that would be plus its amount, which would be M, times its distance, which is just L over 2 squared. Okay, so this would be for the bar. Okay, and then that whole thing would be times omega prime. Okay, so let's look up here for a second, right? I said the V prime was going to be D2 times omega. Well, if I plug that in, let me see if I've got it. I don't think I've got like a highlighter thing here, do I? Let me see if I've got one on the other deal, sorry. Where would this be? Hold on. So now, ooh, look, can you guys see that little spotlight? You see that little red laser thing? Yeah, that's pretty fancy, huh? All right, so now I got to see if I'm ever going to go back to be able to write again. Now, why did I do that? Oh, yeah. So right here, you've got this V. Oh, now I'm writing as well. That's weird. If I don't hold it. Okay, so there's the V prime, right above, right above my pointer, right? So if I look here, right, I'd have to do kinematics. Thanks, Bryson. So the V prime is here, right? If I come over and look at this guy, right, then I have, well, V prime is equal to D2 times this omega prime, right? Well, you see how this is the V prime, right? Here's the L squared over plus R squared square root. And you see how those tie in, right? So it ends up being the same thing, right? Because what I plug in for the V prime. So this is really just like the D squared term. Okay. Same thing here. If I want to write, well, what is my VG prime going to be, right? Well, if I do that, it's just going to be VG prime is going to equal L over 2 times omega prime, right? Well, do you see how that ends up being the same here? So I've got L over 2 here. I got L over 2 here. That's just L over 2 squared, which is right there. So I get the same exact thing. Yep, and like Matt's saying, it's a perpendicular distance, which is this distance right there, right? So it's going to the center of the sphere. Okay, so I got time for a couple more quick questions. What else do you guys want to chat about? Is this one okay, Bryson? I think you would ask this. Does that make reasonable sense to you now? Great. I'm not sure what you're asking about. Which slide are you talking about, Matt? Okay, give me a second. Slider. And is this the one from that's on the page that I gave you? Okay, give me like in class, you mean? Okay, let me see here. Open that guy up. Okay, give me a second here. So point C is 2 pounds. Oh, gotcha. So yeah, we start setting that up. I probably won't quite have time to go through it all. Let me see here. Let's add page. So I'm going to get rid of the spotlight for a second, though. Oh, no, can I? Okay, so let's see if I can. All right, so in this one, right, this is one of the problems that we, where we had it being as a, oops, let's see. The linkage shown, right? So we're given that linkage of AB, and then that we have to then go through the equations to set up to know the forces exerted on bar BCD by the pins. Okay, so this one is actually a little bit like, I can't remember if we did that full crankshaft piston one or not, but so what type of problem do you guys think this one is? The hard type. Okay, so we try to do some relative motion. So do you think we're going to care about forces or not? Yeah, and is it going to be impulse momentum, Newton-Euler, or working energy? Yep, so I agree it's rigid body. Yeah, it's that. So this one's, sorry, it's on the sheet there, Leah. So it's for the linkage shown. It's rotating with a constant angular velocity of 6 radians per second counterclockwise. The slender rod BCD weighs 10 pounds, and the collar that bar BCD is attached to at C weighs 2 pounds. Neglecting friction, set up all equations you would need to determine the components of the forces exerted on bar BCD by the pins at B and C at the instant shown. Yeah, so this one's going to be a Newton-Euler type of one, and another thing to kind of look at is kind of this at the instant shown. So it's going to be an FBD KD type of thing. Okay, but the issue, there's a couple issues here, right? Is that you would have to end up how many diagram or how many bodies do I have? So I got 3. So I'm going to have to end up drawing FBD KD for this guy. I'm going to do an FBD KD for this guy, and I'm going to do an FBD KD for this guy. Okay, and in this case, it ends up, since that thing had mass, that it's got a pin right here. So it's going to have like a CX and a CY as well as an MG. Okay, as it goes through. So those are from the pin, and I also have some sort of a normal force that I don't know how much that is, and that's from the bar. So the CX and the CY is from this pin here, and how much is acting on due to really the bar BCD, and then the normal force would be because it's on this, is constrained to this bar. Okay. And then what would I put for its kinetic diagram? Yeah, so we're going to get to so it has a CY because it's got this weight as well, Luke. Right, because it's got to have a CY. You could think maybe it wouldn't have a CX, right? So if it was massless, it wouldn't have a CX. Okay, but because it has mass, it's got to have a CX because something has to be there to accelerate the mass. Right? Otherwise, there's no other force. Okay, and I think, I'm sorry, I wasn't even looking at all my solutions. I may not have all these exact same amounts. Okay, so then you're actually going to have to go through, and in this case, it actually ends up that this guy up here was just really telling you what the kinematics was going to be like since it was constant. And then you'd have to end up drawing these guys, which is, you could do like a, so this is going to be, sorry, I don't know what happens sometimes when I put my fist down, I just sort of draw, it makes the thing draw bigger. But, oh, actually you were right, Luke, because I drew this screwy, didn't I? I drew wrong CX and CY, so yeah, you were actually right. All right, so that would be a CX and that would be a CY, so they'd have to be equal and opposite. And then this guy would be a, like we'd have a BX and a BY there, right? And then this guy, we would have an AC and the X. And then in this case, I don't think the C was at the middle. So basically down here, we'd have a G. We'd have to go through here. We have an IG alpha, and that's of BC, and then I'd have an AG, an MAGX, and an MAGY, and then I'd have an MG term here as well. So I think actually I drew pretty much all those things on the solution approach deal. Okay. So then basically you're just going to have you have a ton of equations and a ton of unknowns here. Those are your FBDs and your KDs. But now this thing right here, right, if you look at this equation, or I'm sorry, this linkage, it's giving you the 6 radians per second. So you can go through all your kinematic relationships. So you could go through and say, well, velocity of B is equal to the velocity of A plus omega AB cross R of B with respect to A. right? And you know VA is 0, right? And you actually are given omega AB. So you can get VB. And now what do I want to relate that to? Well, I'm going to relate that to VC. So I say VC is equal to velocity of B plus omega of BC cross R of C with respect to B. Okay. So out of these two equations, right? Because now basically what I have is omega AB cross RB with respect to A plus omega BC cross R of C with respect to B, right? And I know that VC is constrained to the x direction like Luke was saying before. So out of this whole relationship, I get omega BC, like we did through those different rigid body problems we've done before. Does that make sense, everybody? That's correct, Aaliyah. Yeah, so this is essentially what is V of B with respect to A, right? So these two things are the same. Okay, then you'd have to go through the whole, right? Because really, in the end, we want to know what we always want to know about accelerations. So I'm also then going to have to do, well, the acceleration of B is equal to the acceleration of A plus omega, and that's omega AB cross omega AB cross R of B with respect to A. Right, and we know what these are, right? And then we're going to do plus alpha AB cross R of B with respect to A. And what's alpha AB? Yeah, and that's because this 6 radians was given as a constant. So that one's 0. I know A of A is 0, and then I'm going to have to do the same thing where A of C equals, and you're going to have to do all that stuff out as well, right? So from all those kinematics, then you're going to end up being, from all that kinematics, you're going to get your alpha and your omega. You're going to be able to solve for all your different accelerations using kinematics and then solve these guys. Yeah, Bryson, so some of the other folks had decided, they thought, especially because we have a follow-on class that exclusively uses omega cross R for three-dimensional problems. So you can use omega squared R. You have to be careful. A lot of people misuse that, but it's okay, right? But essentially, this is always going to be good for you. So we've decided to kind of start concentrating just on that omega cross R. But it will give you the same thing as the minus omega squared, where R is still a vector, but the omega is just however much, 10 or 20 or 2 or whatever. Okay, so I will also be in my office from 2:30 to 3:30, down in 124B from 2:30 to 3:30 tomorrow, I think is what I had said. So if you want some more work then, that will be fine. And I will also try to see, I should be able to record this, so or it should be posted, but it takes a while for it to all go through. So yeah, thanks for joining in. It's pretty cool technology, I think. So still got a few little bugs here and there. Okay, so I will see you guys tomorrow. Study hard, get lots of sleep too. Yeah, you guys too. Have a good night, Aaliyah.